So this is due to Manin, 1970, and the idea is to use the Brauer group to obtain obstructions to the Hasse principle and to weak approximation. So the setting is as follows. X is an algebraic variety, let's assume projective, over a number field K. And consider an element of the Brauer group of X. And you remember I never quite gave you a definition of Brauer group of a variety, but I told you how to obtain elements of the Brauer group from Galois cohomology. So now, given an element of the Brauer group of X, there are evaluation maps at the points, at the rational points of X. So there are evaluation maps taking rational points to, well, you restrict alpha to that point and you get an element of the Brauer group of the base field. And there's a similar thing at all the completions. So if you have a place nu, then the k nu points upon evaluation give you elements of the Brauer group of the completion. And the now we know that the Brauer group of the completion at a non-Archimedean place is canonically isomorphic to Q mod Z, and at Archimedean places it injects. It's either order 2 or order 1, so it has canonical inclusion map in here. And so we call this composite the local invariant So the local invariant is a way of evaluating alpha at. No, this is the invariant of alpha at a given k nu point of X. So, I mean, yeah, when you use this, you have to make it clear that you're starting with a k nu point. So you have to specify which nu. And then you just evaluate. And we're going to evaluate for various nu. So let's recall there was an exact sequence characterizing the Brauer group of a number field. Well, alpha lives in the Brauer group of X. So if you have a k nu point, then you restrict alpha to that point, and you have an element of the Brauer group of k nu. And then you apply this canonical map to Q mod Z. Okay, so there's an exact sequence. Let's remember this from a few days ago. Brauer K to the direct sum over all places nu of Brauer K nu like that. So what this tells us by this exact sequence So if you take any rational point on X and you look at all the local invariants, so the local invariants Yeah, no, I think now I did run into this problem. I always have a hard time. No, maybe this notation is wrong. I've always had trouble with notation like this. I mean, x is a rational point, so you certainly have embeddings k into all the completions, and then you. Well, anyway, okay, this is a complete mess, like everything I do. But yeah, you sum the invariance of k at I should have checked before coming here. What usually goes in the subscript? I guess there's a chance that I'm using completely the wrong notation. So if that's the case, I'll correct it tomorrow, I guess. I mean, that's my last chance. Yeah, I mean, if I can even prepare a lecture for tomorrow. At this point, I have nothing. I have nothing to tell you tomorrow. Hopefully, between now and tomorrow this time, that will change. So I've messed up this notation, and also yesterday I messed up a hypothesis. So yesterday I thought maybe we had to add smooth to a hypothesis. Well, you don't need it. So where I wrote smooth with a question mark, you can cross it out. Okay, so anyway, the point is not the notation. The point is what's going on, which I'm doing an absolutely terrible job of explaining, which is just that the local invariants at the various completions have to sum, well, k nu, have to sum to 0. Because, well, just by that exact sequence. So if the possible local invariants if they can never sum to 0, it follows that there are no rational points. So, well, let me do an example. I mean, maybe, especially since the notation is such a disaster, at least in an example, it's just everything is concrete, so I won't get messed up with notation. So it's the same example we've done. So we did it first using Hilbert's symbol as an exercise, and then second we did it using torsors, and now we'll do it using Brauer Manin obstruction. So this is okay, and then I'll state the formal definition of the Brauer Manin obstruction. But that's just a bunch of symbols, so you wouldn't see what's going on. Maybe in the example you see what's going on. So we take the element of the Brauer group, which we wrote in two different ways. I mean, it's the same element of the Brauer group, just two representatives. So, yeah, now what do I want to do? We have to do some local analysis, so two-adic analysis. So if you look at two-adic points, yeah, I don't know. I mean, you sort of, on your own time, you try even, odd, all different possibilities, and you see that y has to be odd. So this is the usual convention that you hypothesize a two-adic point UVXY with UVXY all two-adic integers and at least one of them odd. So it's the usual thing where any common prime factors get divided out. So then under those hypotheses, y has to be odd. And then you see that forces either this one and yeah, and I think x can't be odd. Is that the point? Well, anyway, it's a different possibilities, and I mean, it's well, I'll just write down what's true, and then 1 of x squared minus 2y squared and minus x squared plus 3y squared is this even right? So I guess x, yeah, y odd, x even, I don't know. Yeah, I mean, maybe, anyway, I can't do this, but anyway, so it's something like 3 mod 4, and so the local invariant is always 1/2. And then p-adic analysis. Well, you're always just completely unramified. So again, there's some analysis which, I mean, if you've done it as an exercise, then you see how to do it. But if I stand here and explain, well, I'll say mostly wrong things, and you won't see it anyway. So you just have to, try possibilities. I don't know, mod 4 or mod 8. You have to usually go to some precision like that and see what's possible in this case. And here it's an easy argument because p can't divide both factors, because then p would divide x, p would divide y, p would divide, well, what? No, you have to break into 3 mod 4 and 1 mod 4 or something, but it works. So, yeah, anyway, I'd get it wrong if I tried to explain. So what do we have here? Oh, I forgot real. So real, and then it's the same thing. So the point is these don't vary. I mean, there are lots of 2-adic points, but they all have the same local invariant, and same thing here. So you always get 1/2 plus 0, and that's it. So now let me state it formally. So it's if for all adelic points. Have you seen this notation for adelic points? I assume you have. I mean, this is just the product over all completions of adelic. So if for all adelic points there is some Brauer group element such that the sum of local invariants is non-zero, then no rational points. Oh, no, yeah, alpha's in news again. Okay, so where? Here? Yeah. That's a nu. No, oh, that's a k. Oh, okay. Yeah. Yeah, it's well, at least one. I mean, there has to exist some alpha. For every adelic point, there is some alpha. There exists some. Yeah, for each. For all, for each, it's the same. For each adelic point, given an adelic point, there is an alpha. Alpha might depend on the adelic point. Okay, now so let's see, two remarks. Okay, the first is obvious and the second is a little bit less obvious. So the obvious remark is that if you change alpha by an element of Brauer K, then the sum of local invariants is the same. Well, I mean, you just see it by the exact sequence. And the second remark says that essentially there's only a finite amount of work to do. I mean, there are infinitely many primes, but you can ignore all but finitely many of them. And as for each alpha, so yeah, for each Brauer group element, there's some finite set of places where you have to do work, and at all the rest of the places, the local invariants are all automatically zero.
Are those places limited to the places of bad reduction, or can they be good reduction places as well?
Essentially, they're the bad reduction places. I mean, you can be stupid with your alpha. You can take a good alpha and then add some random element of the Brauer group, which ramifies at some big primes. But, I mean, it's, yeah. So the question is whether these are only the places of bad reduction of x. So it depends on alpha. And so so you have to check all the places. Let's see. You have to check all the Archimedean places, first of all. But there are finitely many of those. And you have to check all the places of bad reduction. There are also finitely many of those. Now, of the remaining places, you have perhaps finitely many more where the alpha, even though x has good reduction, alpha fails to reduce to a Brauer group element of the fiber. So you have, again, finitely many of those. And that's all you have to check.
So the condition of the Brauer Manin obstruction can be checked in finite amount of time?
Yeah. So that's, in fact, my next remark. There is an effective algorithm. So, but again, you have to be a little bit careful with statements like this, because this statement is true in the context I was working the day before yesterday, where the Brauer of X was identified with a Galois cohomology group. So remember we had hypotheses. So no, this is getting ahead. Well, okay, I'll state this now. So K, a number field. And then we had these hypotheses. We assume that over the algebraic closure, the Brauer group is trivial, and that the Picard group is finitely generated. And so these conditions, hold whenever so there's a large class of varieties, rational varieties, for which you automatically have this. Okay, so then under these hypotheses, we had essentially, well, so these we saw implied that Brauer X, not Brauer K, is isomorphic to and this way you can reduce to a finite Galois extension, so finite group, finitely generated module. This is a finite group, so you have finite number of classes alpha. You only have finite number of news to check, and then there is an effective algorithm. To check whether there's a Brauer Manin obstruction. So I think to compute.
As I know, one of the
Yeah.
It hasn't any fixed algorithm, but I think that from these remarks, it should have an effective algorithm.
Its p-type group is not finite generally.
Okay, there is also a Brauer Manin obstruction to weak approximation. So there's a statement called weak approximation, and I'll state as follows. So you define so we know what adelic points are, and then you define XAK Burr to be the set of adelic points that are not obstructed by any element of the Brauer group. And then, well, it's again a consequence of the exact sequence we had, that x of a of k is contained in this closed subset of the full set of adelic points. And why it's called obstruction to weak approximation. So weak approximation in this language, these language of adelic points, is the statement that so weak approximation holds is when the closure, so there's a topology on x of ak. It has the product topology. And when the closure of the set of rational points is the set of adelic points, then we say a weak approximation holds for x. So this is weak approximation holds for x. And then there's, well, there are a lot of x for which this fails. That's the point of this. There's an obstruction to weak approximation. So then the next thing you might hope for is that you have equality here, taking closure. So that would be the statement that the Hasse principle is the only obstruction to weak approximation. This Brauer Manin obstruction. So this is Brauer Manin obstruction. Is the only obstruction. To weak approximation. So you see that statement in the literature, and it means exactly that adelic points can be approximated by rational points exactly when they are orthogonal to the Brauer group. And so just to see a concrete example of this, if we consider something like u squared plus v squared is t squared minus 6 and plus 6.
So sorry, by the way, so Brauer Manin obstruction refers to that XAK Brauer might not be dense in XAK?
This might be a strict inclusion, yeah.
Okay.
I mean, in general, yeah. This in general is a non-trivial condition. I'm going to give you an example here. So, yes, each of these conditions is closed, an intersection of closed sets. Okay, so let's consider solutions u, v, and t with t an integer. Just to simplify the analysis. Of course, if t is an integer, then here you're asking which integers are sums of squares, and then if it's a rational sum of rational squares, then it can be written as the sum of integer squares. So I could just write UVT, all integers. But anyway, just so focusing on t being integer, then we must have t equal to 1 of 0, 1 or 5. Mod 6. So you see here a condition that can't possibly come only from the local analysis, because you're mixing what happens at 2 and what happens at 3. And so this is an example. And you can work, this is very similar to other examples we've done. You can work this out on your own, and you'll see that there's an element of the Brauer group and a condition like this, and that restricts you to 3 residue classes, mod 6. Okay, so let's look back over here. So I said, yeah.
So the statement that, does the approximation hold for all x or for, what is the statement?
No, I mean there are theorems for certain classes of varieties, like hypersurfaces, say of given degree in, I don't know, in a big enough projective space, then weak approximation holds. Or for, so did I mention last time, equations like this. So when you have u squared plus v squared equals p of t. So I think I quoted a result of, do you have it in the notes from the very end of yesterday? I quoted a result and I said this was an application of the descent method to write down equations of universal torsors and then study the geometry of these big torsors and try to prove the Hasse principle or try to prove weak approximation for them. And then I quoted a result by Kolio-Telen. Okay, I'm going to be caught. I can't remember. Kolio-Telen, Sansuk, Swinnerton-Dyer, and what year? 87. And it said that when you have a degree 4 polynomial, then, well, all I said yesterday, because we didn't have this language, was that we understand the rational solutions. But the precise statement is that the Brauer Manin obstruction is the only obstruction to weak approximation on such, well, these surfaces have a name. They're called generalized Chatelet surfaces. So, generalized. And then, in fact, when P is irreducible, you can show there's no Brauer Manin obstruction. And so for irreducible P, in fact, weak approximation holds. You have equality here. And then there are examples like this where you have a strict inclusion. So yeah, so that's an example where we know weak approximation. Okay, now let's return to this statement here. So I said that when you have some conditions like this, so that these, you have only finitely many conditions cutting out this XAK Burr locus in the set of adelic points, then there's an effective algorithm. I mean, I should really put quotes around this. Because, yeah, you have to have more data. For instance, you have to have your hands on a set of geometrically defined divisors that generate the Picard group. So yeah. But yeah, if you have this condition, you have this in some concrete way, then this can be computed effectively, and then there are effective algorithms to represent elements as Brauer groups use some cohomological interpretation. So you write down co-cycle data for Brauer group elements, and then everything can be done effectively. But it's by no means easy. But there's one case where it is easy, and this is so it's easiest when this group is 2 torsion. And generators can be represented by quaternion algebras. So these are two non-trivial statements. First of all, in general, you do the computation and you get 3 torsion, 4 torsion, or something else. And then, even if you have 2 torsion, there's no theoretical fact that guarantees that a 2 torsion element of the Brauer group can be represented by a quaternion algebra. You have to, in some sense, be in a lucky situation. And that is, that's the situation that Yuri Chinkel and I were in when we did some work. So essentially, we were able to work out some examples. So I think now I'll give a detail of an example. And then I'll describe the general phenomena that we observed. So this was for this I was talking about 2 days ago. There certainly are, but I don't know. Yeah, in this context, I don't know of any. But, in general, you can come up with X, so. So, remember we were talking about the Del Pezzo surfaces. And remember, this is, in this case, K is Q. Okay, so what I'll do now is give a detail of how the analysis worked in one example. Okay, so in this case, we have a splitting field. So you don't need 4th root of 17 to define the exceptional curves. You only need square root of 17. And so this is degree 8 extension, Galois group. 3 copies Z mod 2. Okay, so now so this group can be computed easily enough. And also 3 copies Z mod 2 for M. M is the geometric Picard group. Okay, now if you just do the most naive thing and work with the group cohomology for this group of order 8 and directly convert it to a division algebra or to a central simple algebra, you would get actually a matrix algebra over a division algebra. You would get something, actually I don't know what you would get. Maybe I wouldn't want to do it, but you might get something like a 4x4 matrix algebra over quaternion algebra, and then you would sort of, you wouldn't know how to find the quaternion algebra. You wouldn't even know what it is. You would just be staring at a big 64-dimensional central simple algebra, and it's pretty hopeless. So what you do is you use the inflation map of group cohomology. So this is a map from H1 of a quotient group and the module of invariance to the full H1. And what this corresponds to in this case, so H corresponds to some intermediate field, and what is it? In this case, it's just, let's call it F. Okay, so then you have the extension there. And then M is the geometric Picard group, which is all defined over K. And then M H is the Picard group defined over the intermediate extension. So we're taking an intermediate extension. We're taking the classes in the Picard group that are defined here. And it's now a smaller problem in group cohomology. And it turns out for one choice of index to subgroup H, this is an isomorphism. Now again, there's no theoretical reason why this should happen. It's a phenomenon that we observe. Now, you go back to the Leray spectral sequence, the one that tells you have an isomorphism here. And you see what it tells you in the case of the smaller extension. Use the Leray spectral sequence for the extension f of Q. Okay, and it gives you the following exact sequence. Now what did I, so let's call this Q. So Q will be the quotient group. And then the inflation map, just put it alongside the other. So this is the inflation map. Okay. Now this is this is exact, but here there's a nasty H3 group. And now which is it? It's H3Q, values in F star. So there's potentially an obstruction to taking an element of H1, of the smaller H1, and lifting it, so representing it as an element of the Brauer group that's killed upon passing to the extension F of Q. So we have this obstruction here, but Q is cyclic. So if you remember from group cohomology, there was an efficient resolution that you could use for cyclic groups. And this gave you a complex that was just M at every place, and the maps alternated. So H3 is the same.
Q, so this is not rational numbers, but isn't certain cases? Or?
No, well, Q. I hope, yeah, is it confusing?
Well, just where do we define Q then?
Q is, yeah, I wrote it kind of slow.
Oh, that's Q.
Q. So Q is the quotient group. So this H3 is H1. And H1 of the multiplicative group of a field vanishes by Hilbert 90. So in this particular case, the obstruction vanishes. In general, you might have to deal with it. So you might have to enlarge the field to kill the obstruction. But in this case, we can directly lift the elements here. And so we're able to find quaternion algebras. Now, did I tell you what the field is? Did I ever write? Probably not. I probably never wrote that in this case, F is, so this choice gives F is Q adjoins square root minus 17. Okay, so your quaternion algebras will be minus 17 and then some rational function. Okay, so then so just to tell you how, I said this was 3 copies Z mod 2. So this module here, so the Picard group, in this case, we have 4, so it's minus canonical class, so it's rank 4 in this case.
So how do you gauge the surjectivity of inflation?
Which one? On top?
This one,
Or-
the
Which line? The bottom line or the?
surjectivity of inflation.
Oh, why is it?
You want the surjectivity, right?
It just is. I mean, there's no, we just compute. We just try, we try all index 2 subgroups, and compute and
Was there any guarantee that such effect exists?
no guarantee. It just happens. So we have this, and here, so this is obviously Galois invariant. So and the Galois action sends each di to minus di. And then, yeah, so it's easy to see that if you compute this and you get 3 copies, Z mod 3. Okay, so the procedure, find, what do we want? Find the divisor, find the and then find a rational function. So let me use this notation, Galois conjugate. So this has class little di, this has class minus little di. So this, well, as is always the case for the divisor associated to a rational function. It's something whose class in Picard group is 0, but we want it to be this divisor. And so then minus 17 Ri represent so I equals 1. Okay, so now, I mean, it's a concrete problem now, but it's still a problem to be solved. So let me explain how we do this. So, I mean, we know all these classes. We know what the little di's are. We have a basis. We work with a basis, and we have written with respect to a basis. So that's a basis of classes of exceptional curves. And the exceptional curves, we remember, are defined over the big field. They're not generally defined over F. So, yeah, we don't have exceptional curves. We can't find any union of exceptional curves that has the right class in Picard group. So we have to work a little bit. And so to produce di, we use descent. So we know how to solve the problem up here. So we start with so L and M are 2 exceptional curves. Over the big field is big K. send line bundle O to F. So this is O F. And then once you have the line bundle of the correct class in the Picard group, then you take a general section, you look at where it vanishes, where it has poles, and the difference then gives you divisors of the correct class. So, and then, yeah, I think then you can figure out how to find a rational function that vanishes on a given divisor. In other words, how to explicitly realize a divisor as rationally equivalent to 0. So that's essentially what we do. And so the result minus 17, and then some expression that actually isn't so bad. And the sign at the end actually doesn't matter. So, and you cyclically permute the variables and you get the other. So this is one generator, and then you have two more that you get like so. No, you have to show it. I mean, it's part of the computation. I mean, there's some symmetry. I mean, there's actually a full S3 of symmetry of this Del Pezzo surface. So you know that it would, well, anyway, you trace through how the symmetric group acts on the Picard group, and you see that it gives you at least the same element of Brauer X mod Brauer Q. So it differs by an element of Brauer Q. And in fact, you show explicitly. And this is all part of this, the general way of working with Brauer group elements. You can show explicitly that it's on the nose equal in the Brauer of X. Yeah. So I made this cheat once before. Yeah. So the whole thing should be divided by, you take your pick, x to the fourth, y to the fourth, z to the fourth. So if you multiply either of these by a square, it doesn't change anything. So yeah, you put anything in the denominator. And okay, so now let me just complete this example and tell you what the result of the local analysis looks like. Okay, so we have three classes in the Brauer group. And we have 3 primes. We have to consider Q2 points, Q17 points, and, well, the Archimedean place. So R is the easiest. This expression is always positive. So or no, it's not always positive. It depends. Yeah, it depends on the sign of W. But at least it's the same, all positive or all negative. So all ramified or all unramified. So this is some terminology you often see. So unramified would be trivial, and ramified would be non-trivial. Okay, at the prime 17, it's again all ramified. At Q2 points, it always splits up. So of the three classes, at every two-adic point, two of them are ramified. And one is unramified, always. So the result from this, you see, is that there will always be at least one of the classes for which the local invariants have non-zero sum. So okay, and I think I'll just quickly say, extremely quickly, I have like 2 minutes left, say how the analysis goes in the generic case.
By the way, for the ramified cases for Q2 and Q17, what are the invariants of those places?
Well, it's always 0 or 1/2. See, it's a quaternion algebra, so it's always two torsion, and it's either, and it's, yeah, we're just using this notation where the local invariant takes a value in Q mod Z, so 0 or 1/2. Okay, so generic case. Remember, that's the generic alpha group was order 128. And then it turns out that, again, the inflation map, so for a particular index 2 subgroup, the inflation map is an isomorphism, and this, in fact, corresponds to the quadratic extension Q adjoins square root minus ABC of Q. And for the same reason as before, this nasty H3 group vanishes, so you can carry out explicitly. And now this D, well, there's no need to have an index. There's only one of them, because then this, I said this last time, then it's 2. So then this D, this divisor that entered into this program here, D is a preimage. So remember, X is a double cover of P2, branched along the cortex. And D is a preimage in X of a conic in P2 meeting the quartic in 4 tangencies. And it turns out that you can always find such a conic defined over this extension field, and that gives you your D. And then as before, we compute R, we get quaternion algebra minus ABC R, and then we have examples, we have one example where, again, there is an obstruction to the Hasse principle coming from the Brauer group. I'll stop here.